So we call this technique interrupt-oriented programming. This came from, Sergey moonlights as an academic. So as an academic, you can't call it an exploit. You have to call it oriented programming. And they have this whole distraction about Turing completeness that we can thankfully skip over because we get remote code execution. And you can't argue with a root shell.
You can't. But just in case you're wondering where this interrupt-oriented programming belongs, well, you mostly just craft data and send it to targets, and that's your exploit, right? So first you used to craft your shellcode, right? Executable shellcode. Then NX and DEP happened, and then you had to craft your return-oriented fake stack frames, and that's your return-oriented programming, which academia discovered 7 or 8 years after it was actually published in FRAC.
I thought it was a full decade.
Depends on how you count.
Okay.
But if you, in Hera's bug track post, it was actually more like exactly 10 years. And then you have and then of course ASLR came into the picture, and you have to bring your own linker, which contains an info leak in order to find that address and then link against it. And this is your BYOL. Now imagine that you could send no data to the target whatsoever, right? What could you send to the target? That would be our interrupt-oriented programming, which is, of course, a pun on the return-oriented programming.
Now, just to be clear, when we say that we're sending no data to the target, we don't mean that we have no control of anything inside of the target. We're doing this as a Bugdoor. So we are sneaking a little bit of code in there, but our initial case was, you've heard of a Stack Overflow exploit. This is a stackoverflow.com exploit. What we do is we post a fake tutorial for how to use interrupts on a microcontroller, and then we wait for people to use the bad advice in the tutorial. And when you do it this way, you have no behavioral side effects. So if you insert my Bugdoor, your chip will still work. Second, it's in the most confusing part of the proper way to write an interrupt for this platform. So I can deny that I made a mistake maliciously. It was an honest mistake. And third, this is the thing that you are most likely to ask for help with when you're new to this architecture. And this is architecture specific. We're doing this for the MSP430. So whatever experience you have on x86 or ARM or PowerPC or MIPS or Spark is irrelevant here. So even if you're really good, you're still going to Google for the one piece that you don't yet know.
Yeah, see, this is the Internet of Things that, you've never touched before. So, first of all, it has to be small. And second, you can't send any data to the target. What can you send to the target? Why, you can send interrupts to the target, right? When you send an interrupt to the target, and just think of a signal sent to that little processor leg, because processors are like those little bugs, right, with legs sticking out, and just connect that line, and send it there, and it sends the processor executing code from somewhere. So you're affecting its state, but you're not sending any data. You're just sending this pulse. Your entire program is a series of well-timed pulses.
Now, you have some advantages on your end. When you're attacking a server, it's off in another country somewhere or in a locked data center somewhere, and physical attacks always work against a server, but they're kind of irrelevant because you don't get to use them in the real world. When you're attacking a microcontroller, you're in the opposite position, in that the victim is the manufacturer of thousands of devices. The attacker purchases 3 or 4 of them, brings those to a private laboratory, and is able to stick needles into them, is able to connect all sorts of fancy test hardware, has local physical access. Also, when you're attacking popular software, let's say you want to bug in Apache, well, you just download Apache. If you want to bug an IIS, well, you don't get the source code, but you still get a binary, and that's almost as good if you're willing to be patient. For a microcontroller, you don't get a copy of the firmware for free. There's no such thing as a free lunch here. So what you have to do is you have to rip it out of a locked device. Our Bugdoor is a 4-instruction change to a common interrupt handler that, combined with existing natural pieces of the firmware, allow you to elevate your privileges, enter the bootloader, and then exfiltrate a copy of the firmware from the device, along with anything else in flash memory, like keys or certificates or that sort of stuff.
So it's important to understand that you have physical access. You actually got the chip, and you maybe got similar chips as well, and you can mount them, but you can't decap them, and you can't stick microprobes into them. You can run them at lower clock speed. In case you're wondering what that hotel logo is doing there, that's where we came up with that. That hotel in Amsterdam, the Rue de Leuve.
So the basic idea is that just as if you were writing an exploit for, when you do a simple exploit, like a stack buffer overflow exploit, it's just called the exploit. But when you're doing a more complicated one, or one that has to be performed in stages, like a heap exploit, you have different primitives. A write anything anywhere primitive is as good as it gets. That lets you overwrite any object you like. But sometimes you have less powerful ones, like sometimes in writing a heap exploit, you'll have a string comparison that's just a little bit off. So all that you're able to do is overwrite 1 byte after the string with a 0. That's a less useful primitive. So we wanted to reuse as many natural primitives as possible, and then make the smallest change that we could possibly do to backdoor the interrupt handler.
And so the simplest thing that you can do is you can enter an interrupt handler and then interrupt it again. So think of the gadgets, right, that you use in return-oriented programming. There, you jump into the tail of a function where you're not supposed to do that, and then return back on the return the way you're supposed to come back. Here, it's the exact opposite. You enter where you're supposed to enter, and then you can leave at the instruction of your choosing. Now, remember, those are microcontrollers. Their clocks can be slowed. So you just need to be able to nest those interrupts. And doing the same thing over and over again, and leaving it a few instructions later, you get to accumulate some state in the processor. Because a reset is not, the beginning of a new life. It's just a jump. So this is how you do that.
So this is our target hardware. There are other ways to attack hardware, of course. So the JTAG pins are here at the top. We're not going to use those. We'll use them for development, but our end exploit has to be triggerable without access to those, because there's a fuse that can block that. There's a great way to bypass the fuse protection. You just remove the lid of the chip with nitric acid and hit it with a camera flash 4 times. But you can't always rely on that, so we're doing a different exploit here. Those 2 pins that you see just beneath the model number, that is the reset pin, which is also known as the non-maskable interrupt. When you hit this, if the chip has been properly configured, instead of restarting the chip like it does at a power-up, it will instead call an interrupt handler that has priority over everything else. This is the one that we're backdooring in order to control stack depth.
Those 2 pins are your programmable interface. That's all you get to talk to the processor.
This is a 16-bit RISC architecture. Because it's RISC, every word on the stack is word aligned. So they all have a 0 for the least significant bit of the address. And just like on x86, the stack grows downward. Now, normally, an interrupt cannot interrupt itself. But a lot of this is your responsibility as a programmer. For example, when you receive a byte through the UART on this chip, you have to clear a flag that says that you've read that byte and it's safe to load it with another. If your UART handler takes too long, your serial port handler takes too long, you might actually miss bytes because the machine can't load them into the buffer fast enough. So where you clear these flags inside of the interrupt matters a lot, and it's implemented differently by different chip manufacturers. So Texas Instruments does it one way, Atmel does it another way, PIC does it a third way, and this is before we get to the complexities of ARM. So our patch makes it so that this interrupt handler can interrupt itself. And we do this by accidentally clearing the wrong bit. So the way that this works is that the attacker now has a primitive that can cause the stack to grow as deep as he likes. You can grow it down 10 bytes, you can grow it down 12 bytes. You're still limited by the size. This grows by 4 bytes every time you trigger it. So we'll combine it with another primitive in order to control the alignment. Now, this allows us to point down to the BSL. The BSL is the Texas Instruments proprietary word for the serial bootstrap loader. This is a ROM image that is 1 kilobyte that contains a bootloader so that you can program the chip over a serial port without needing a JTAG debugger. This thing is very handy. It also has a couple of vulnerabilities. One of the niftiest things about it is that it has 2 different entry points. The first entry point is called the hard entry point. That you can always access externally, and it forces the chip into the bootloader by starting from there instead of starting from the normal reset vector. The second one is called the soft entry point. The soft entry point is not documented, but it is used by some Texas Instruments firmware, and it's very easy to find it when you're reverse engineering. The soft entry point does not change the register that contains a flag specifying whether the password has been checked. If you put a 1 into this register and you bounce through, it gives you administrative access to the chip and you can read anything you like. So what we do is we use the stack growing primitive to just keep pushing the stack down until it's here inside of the ROM. When the stack is in ROM, well, ROM is read-only memory. And this is a microcontroller. This doesn't have a fancy MMU. So when you write the return address onto the stack, the write gets silently ignored. When you pop that value back off the stack, it's the existing word at that location that is read back. So by pointing at the right spot in the bootloader ROM and then returning, you're able to jump the program counter so that the chip then begins executing code from that address. So we injected a stack growing primitive. We then rely on triggering this inside of natural code when a bit is set in register 11. Register 11 is a scratch register, so every function does something differently with it. So we use the serial port to talk to the existing firmware until a scratch variable has 1 bit set. This is on average about half of functions that have 2 local variables. And then we can bounce down and we can control the value of register 11 by when we begin to run our exploit. We also control the stack alignment by a natural interrupt that cannot interrupt itself, that it has an extra local variable so the stack is a little bit larger. And then third, we control the stack depth by how often we trigger our nested interrupt. And then it's a trap. And then we have gotten the chip to execute its own ROM image as our payload without requiring any external, without requiring any changes to the firmware other than 4 additional bytes. We implemented this Bugdoor for an embedded operating system called TinyOS. Now, TinyOS is often used by copy and pasting. Like, there are lots of commercial products that have forked off of this. It doesn't really have a kernel. Instead, you compile all the source code together. But they're really happy to accept patches for new devices. So what you can do is you can make a driver for a new radio chip. And in that driver, hide the backdoor. in order to sneak it into every user of that embedded operating system, who will then inherit the vulnerability, allowing you to dump any of them.
And these are the instructions.
Yeah,
I
so
mean, it's really not sophisticated. What happens is on entry to the NMI, the hardware resets a bit that actually does not allow the interrupt handler to be interrupted. We're clearing that bit.
And the end result is that those 2 lines of C code or these 4 words of machine language are the only evidence of the backdoor. And it's something that you can, with a perfectly straight face and without anyone being able to prove you wrong, you could claim was an honest mistake. Unless they knew that you came to this lecture. So thank you kindly and have a good night.